Okay, so I think we should start now. So good afternoon, everyone. And as you know, this is the session for MLT week 7, and we have done softmax regression in the last session, I mean the Monday session, and we have left with two more topics that are covered in week 7. One is generalized linear model, and another is KNN. So that these two topics we are gonna cover in this session, and then we will see the Colab files that are covered. Okay, so the Colab file, we will generally go through the Colab files, and then in the next session, the solve with us session, we will code those kind of codes in that session. So that will be beneficial for all of us. Here in this session, we will just try to go through the codes. So that will help to understand the concept of KNN and generalized linear models. Okay, so we start now. Okay, so let's start. So how many of you have gone through the content, haven't gone through the content on week 7? I hope all of you have gone through and you have already seen that software regression that now we are not going to cover. We are going to see that software regression using the generalized linear models, how that software regression is a part of generalized linear model. So what is generalized linear model? What is generalized linear model? Okay, so it's the so what we have done till now in the you have seen in the linear regression and logistic regression. Okay, so you have seen in the linear regression what we have done. We have started with the assumption that the data follows normal distribution because all the values are coming from the real numbers, right? All the values are coming, the output are coming from the real numbers. So that we make assumption about those outputs that probability of by given x follows normal distribution. Same for the logistic regression, since in the logistic regression we only talk about binary classification problem. Their classes are 1 and 0. So we make assumption about the data set that the p by given x follows binary distribution, right? So these assumptions we make about the linear regressions model and logistic regression model. What about in general? If we talk about in general, if they don't follow normal distributions and Bernoulli distributions, what if they follow other distribution? Then how we will model those kind of situations, those kind of data set? How we will make the model, right? And here we make the assumptions that the features are linearly related to the I mean the labels are linearly related to the features, that it by is linearly related to the features. And these assumptions we make, and we try to find that we try to fit this model. And fit means we try to optimize our loss and try to find the optimal values of those weight vectors, right? So this is what generally we do in any kind of supervised learning algorithm, right? So we are gonna generalize these things now. We have make some assumptions. Now we will make some okay, give me 1 minute. Okay, so sorry for the interruption. So now we are gonna generalize these things because we have made some particular assumptions about that it follows normal, it follows Bernoulli. Now we will make some we will generalize these things. Okay. So before generalizing, let's cover what is when we call that some distribution follows some data follows normal distribution. So it means that the PDF of that particular distributions is 1/2 root over 2 pi sigma square e raised to power minus by minus mu square upon 2 sigma square, right? So we check the PDF, or if it is categorical, we check the PMF. It follows some kind of like p by 1 minus p 1 minus y, something kind of where y is 0 1. So while looking at the PMF or PDF, we come to know that this follows normal distribution and this follows Bernoulli distributions. By looking at the PMF or PDF, we can find out whether it follows some which distribution it follows, right? So we will look at some other kind of family of distributions, which is called exponential family, and then we will go to the generalized linear models. Okay, so let me share my screen here. Okay, so can you see the screen?
Yes, sir.
Okay, so first, before going to the generalized linear model, let's understand what is exponential family of the distribution. Okay, so as I told you, by looking at the PDF and PMF, we come to know that it follows normal or Gaussian. So if any distributions, the PMF or PDF has this kind of form, P by of eta is eta here is the parameter which has this kind of form where e raised to power eta raised to eta transpose t by minus a of eta and multiply by b of by. So if the PDF or PMF has this kind of form, then we call that distributions coming from exponential family. Okay, so if the PMF or PMF has this form, then that comes in the exponential family. Okay, so what are these terms here? It is generally just think about the exponential distribution lambda e raised to power lambda x, right? So there lambda is the parameter, x there become that t of y, right? And a of eta that becomes 0 there. Sorry, not 0. We have to lambda we have to take inside, and then some manipulation you have to do, and you have to find out what is a of eta, and b of y will become constant there. Okay, so that comes from the exponential family. Okay, now what is this eta? Eta is called the natural parameters. Okay, so why this is called natural? Natural means it some kind of give the characteristics of the distributions, right? So like mu, mean of the distribution. So it gives the characteristics of the distribution. It gives lots of informations about the distribution. So that's why these eta is called natural parameter of the distributions. T of y is called the statistic. So what is statistic? How do you define a statistic?
Could you just make the screen a little bigger? It's a little small.
Sorry?
Can you make the screen a little bigger? I mean, the words are too small for us.
Okay, let me try. Okay. Actually, I don't see any options to resize it. Is it not visible at all?
No, it's visible. It's just it's too small.
Sir, please check in view. Maybe there may be options. View, go in view and check if there is option any to zoom this. Yeah, there is zoom in option.
Okay, okay. Is it working or not? Yeah.
Much better.
Okay, let me do one more. Yeah, thanks. So Now, yeah, we were talking about this expression, right? This expression. So eta is the natural parameter, T of bi. So what is sufficient statistic?
That is the y hat, is it? Distribution of y hat.
So how do you define a statistic? You must have come across this terminology in the statistics course as well. How do you do, what is statistic? I call it is not a statistics, it's a statistic. How do you define this term?
Sir, this is static or statistics? What is this? Sufficient statistics?
This particular terminology, statistic.
We've come across it only in the context of hypothesis testing, where we have a test statistic.
Yeah. What is that? What is that test statistic?
It's something which describes the data, like mean, variance, or something.
Yeah, what is that? Can you please repeat?
Is it something which describes the data?
Math mode is still coming out, so I think I have to restart my. Yeah. Okay. So test statistic is actually defined as a function of the parameter, or say function of the sample. Okay, that function of the sample actually gives the property about the distribution, of property about the parameters. Let's say we have talked about the estimation problem, right? In the statistics, there we define a function and we call that this will actually give you the estimation for the mean, right? So that particular function that gives the information about the parameter, or information about the distributions, that function is called test statistic. Not test statistic, generally statistic. Okay, so here ty is a function of bi. So bi is the sample, right? So here in most of the cases it can be a simple that data itself, but ty it's a function of the sample. Okay, so it is called statistic. Okay, here a of eta, eta is the parameter, as so a of eta is a function of eta. So it makes sure that this pdf of pmf, if it is pmf, then sum over range becomes 1, or if it is pdf, then the integral over the range, integral of this pdf over the range becomes 1. So this particular e raised to power a eta makes sure that this pmf is valid pmf or valid pdf. Okay, b by again is the terminology, is a function of bi. Okay, so if any of distributions follows this kind of pdf or pmf, then we call that expression that distributions come from the exponential family, right? Okay, so
just
obviously
one, so maybe I have one just fundamental doubt. So when we say the distribution, we are talking about the distribution of the features or the labels?
Sorry, can you please repeat?
So when we say this distribution, right, this class of distribution is in the exponential family, are we talking about the distribution of the features or the labels?
Labels given feature.
Labels given features. Okay.
Yeah.
Okay. Because here I see only probability of y. So
yeah, probability of by labels. Okay, so definitely the T, A, and B defines, if we set different values, then they will come under different, they will come under family of the distributions. Different values will give the different distributions, right? Now we will see that Bernoulli and binomials comes under the exponential family. So what is the procedure for checking? We just check whether PMF has this form or not, or the PDF has this form or not. Okay, so what happens in the Bernoulli? Bernoulli has only two outcomes, success or failure, and probability of success is given as P, and probability of failure is given as 1 minus P. So this PDF is concretely can be written as P raised to power by 1 minus P raised to power 1 minus y. So it's the same kind of thing, because y0 makes it 1 minus v, and y is equal to 1 makes it p. So PMF can be written in this form. Now we will do some manipulation to bring this expression into this kind of form. So form is what? E raised to power something, right? So this form, for bringing this form, I will take log and then exponential, just because I need to make sure that it comes into e raised power something. Okay, it's just a mathematical manipulations to bring in the same form. Okay, now if you look at this thing, so this become p, this become by log p, by log 1 minus p. Okay, so now we have to make sure that 1 becomes function of eta and 1 becomes function of by and multiply by some function of eta. Okay, so that we have to take care of now. So we will make sure that p comes another in one terminologies. Okay, so here if you look at, if you do some manipulations here, so this you can see that it's only mathematical part. So the last expression is come out as e raised to power by log p 1 minus p plus log 1 minus p. So it has the form by t of by, this y becomes t of by, and this become eta, right? And this becomes your a of eta. So what will be eta here? Eta will become log p 1 minus p, right? So this is the natural parameter. So what is this? What is log p 1 minus p? We have defined this terminology, right? P 1 minus p, probability of success upon probability of failure.
Log of odds.
Odds, right? So this is log odds. So log odds actually gives the some characteristics about the Bernoulli distributions, and that makes sense as well, because if we know the odds of the distributions, if it is Bernoulli distribution, and if we know the odds of the distribution, then we can say that the probability of success is higher than probability of failure, some kind of things, right? So here log odds defines the characteristics of the distribution. So this is called natural parameter. So remember, for Bernoulli, the eta comes out to be log odds. Okay, if you manipulate this thing, this becomes 1 upon 1 plus e raised to power minus eta. Okay. Yeah, so just compare these things. By comparing, you can see that eta becomes log 1 p 1 minus p, and the statistics 1 becomes by the sample itself, right? So for Bernoulli, you can just remember what is the natural parameter. That is enough for our case. Now,
Sir, there is eta power t. So what is this? Is this transpose of eta?
Yeah, it is transpose. It's, if it is a vector, if here it comes out to a scalar, so it doesn't make any difference if it is eta or eta raised to power t transpose. Okay, so if it is vector, in some case it may be vector, so there we write eta transpose. It's a transpose. Okay, so Bernoulli's comes from the exponential family. Now we will check Gaussian also comes from the exponential family. So for derivation, we have set the standard deviation to 1. So the PDF 1 becomes 1 upon root over 2 pi e raised to power by minus mu square upon 2 sigma. So sigma square becomes is 1 here. Okay, so same manipulations here we have bring into this form. Now if you compare this thing, this all become function of y. So this become b of y e raised to power ty of eta, right? So eta becomes mean here. So in the case of normal distribution, natural parameter is mean itself. Okay, and the test, that statistic is sample itself. Okay, and this terminology makes sure that the sum, the integral over the range is always 1. Okay, so again, Gaussian distribution comes from the exponential family. So these are of these two distributions are of use for our course. Now, so we have seen what is exponential family. Now our come to the main topic, which is generalized linear models. Okay, so we were talking about what is generalized linear model. We are generalizing our model, whatever we have seen till now, like linear regression, logistic regression. There we make some assumptions. Okay, now we will generalize those assumptions and we will try to find the model for that particular case, in those particular case. Okay. So what happens in the linear regressions? We make that by is make assumption that by is can be expressed as the linear functions or the linear combinations of all the features, right? And GLM again, so it is a linear model again, but here, so here the assumption that we make about the model, we will make it more generalized. Okay. So what are the assumptions for generalized linear models? So let's try to compare these two, linear regression and generalized linear model. So in the linear regression, we make that all the features are independent, right? That is the very first assumption that we make for any model, right? And for the generalized linear model, again, we make the independent, that features are independent, the same assumption. Random is that they follow some distribution. Obviously, they are random. Data is very randomly collected, and so they have some distributions, right? So random means they have some probability distribution. Now, the next assumption that we make about the linear regression is that the labels are continuous, random variables, and supposed to follow normal distribution. So this assumption we make about the linear regression. Now we will generalize this thing. Rather than following normal distribution, the variable y does not need to be normal distributed. It can be any distribution from the exponential family. So now we have generalized these assumptions. Rather than following normal distribution, it can be any distributions that is coming from the exponential family. And we have already seen what is exponential family. And the next assumption that we make about the linear model that we suppose the linear labels has the linear relationship with the features, right? And for now we generalize this assumption. The label need not to have linear relationship with the independent variables, but transform labels. Transform is we make some kind of transform our features. Suppose in the case of logistic regression, where we have labels 1 and 0, but we transform into log odds. That log odds supposed to follow, supposed to have linear relationship with the features rather than the labels itself. Log odds. That log odds is the transform labels. Okay, so transform labels means that we have some function, link function, and after that, applying that function, that transform labels supposed to follow, supposed to have linear relationship with the features rather than label itself. Okay, so logistic regression is one kind of example for that.
Can GLM be also be told that since we do polynomial regression and then come back again to linear regression, can that also be classified as a GLM?
Yeah. So all are the actually standard cases for GLM. Okay. Right, because exponential family, because here all these assumptions are followed by linear regression as well, right? First is clear. Second, we are saying that the distribution is coming from the exponential family, and in the linear it is normal, so it is again the part of the GLM assumption. Second, we assume that the transform level. So identity again is a transform level. So labels supposed to be have linear So has some linear relationship with the features. Again, so this is linear regressions assumptions are followed by the assumptions from GLM. So linear regression is a part of GLM. Okay, both linear regression and logistic regression, all those models are actually the standard cases for GLM.
So is there a separate model for GLM, or is it, I mean, just that?
Yeah, we are coming to that, how to model in this case. Now we have assumptions, now we will try to find how to make the model. Okay. So why GLM? It's very clear because now we have generalizing thing because we have make some assumption that data have some relationship between X and Y that is linear. That need not to be case in every time, right? So their relationship can be exponential relationship, other relationship as well. We can do polynomial transformation. This is again the same part of GLM, but that's why we need to generalize our models. Whatever we have done till now, we are generalizing these things. Okay. Again, labels need not be continuous, right? Remember the logistic regression where we fail to use linear regression model. We adapt the procedure, but the output comes out to be real numbers that we don't want because we want the classes. So getting those classes, what we do because they are categorical variables. So we apply some kind of log odds because labels are classes, and we transform those labels into the log odds. Now we can apply linear regression models. Right, so because log odds can have real numbers rather than only two classes, two categories. Log odds can have real numbers. That's why we have transform our labels into some other categories, and then we are forming the linear models there. Okay, so this is where we need to generalize our linear models. Okay, so that so these assumptions, let's rewrite these assumptions in the better way. Okay, so first assumptions we make that it follows from the data is coming from the exponential family. So that we can write it as by given x, w are the parameters. So by given x follows the exponential family with the parameter eta. This eta is the parameter for that distributions like mean and whatever that is. The second assumption is that, okay, so our goal is to predict the expected value of t of y, right? So this makes sense. We actually predict the expected values. Does this assumption make sense?
Yeah.
How do you predict? You are supposed to predict the expected value, right? Once we know that this data is coming from this distributions, so some new things comes and we don't know what it values will be. So what you will predict for that value? You will supposed to predict that, you will likely to predict that it is the mean of that, right? The expected value of that. That is more likely to be happen, right?
Sir, are we maximizing the likelihood here in any way, or this is something
So
else?
that is the procedure. That is the procedure of how to estimate something. I'm not so here. I'm just saying some new examples comes in. I don't know about what its value is, but I know that it comes from that distributions. So what I will predict about that value, I will likely to predict that it is the mean of that distribution. Let's say my data is coming from the normal distribution, normal 0, and some new examples. I don't know the value of this. So for that, I will say that it's 0. I will assume that it's 0 because it's more likely that it will be the expected value, right? It's the definition of expected value.
Sir,
When you
understand
perform
that,
for
that example.
certain distributions again and again, it is more likely to be close to the expected value, right? So again, these assumptions make sense. So our goal is to predict the expected value T of by given X. Okay, so in most of the cases, T of by is by. So we are predicting by. So our model is actually the expected value of by given S. This is our model. Okay. This is our model. We have by given X. So expected value is our model. And the last assumption that the natural parameters and the inputs are linearly related. So eta is actually linearly related to the features. So this is our last assumptions. Okay, about the GLM. So from these assumptions we can model any distribution, for any training data set which comes from the exponential family. Okay, so let's see how linear regression is a part of generalized linear model. Okay, so it's a special case of generalized linear model. So we will see all three using all these three assumptions. We will come to note that model of linear regression, how you will derive the model of linear regressions. Okay, so what is the first assumption? It comes from the exponential family. And in the case of linear models, our assumption that by given X follows the normal distribution. So this is our first assumption. Second says that the model is expected value of by given X, right? And what is by given X? It is the normal. So what will be the model in our case? It is the mu, because expected value of the normal is mu, right? So this is my second assumption. What is the third assumption? Third says that eta is linearly related to X. So eta is equal to W transpose X, right? And what is eta in our case? What is the eta in normal distribution? Mu, right? And what was mu? Mu was model. So we can say that model is W transpose X, right? So from here we can conclude that linear regression is actually the special case of GLM, right? Now see, all using these three assumptions, we have found out the model. The model in the linear regression is actually W transpose X. Okay. Now let's see whether logistic regression follows the GLM or not. So first assumption, because there are only two categories, 1 and 0. So we can assume that by given X follows Bernoulli distribution with some, okay, so here we need to define the parameter, it's P, right? So what is the second assumption? Second assumption says that our model is the expected value of that distribution. So what is the expected value of by given X? It's P, right? And what was P? P was 1 upon, that we have already seen. 1 upon, in the case of Bernoulli, eta comes out to be log odds. From there, we can find out the value of P. P comes out E upon 1 plus e raised to power minus eta. Why we are doing this? Because third assumptions make some assumption about the eta. So we are converting this model into the form of eta. Okay. So eta, third assumption says that eta is actually linearly related, right? So from that assumption, we can see that the model of the logistic regression is nothing but 1 upon 1 plus e raised to power minus eta x. So using all these three assumptions, we have seen that logistic regression is again a part of generalized linear models.
Sir.
So any questions up to here, till here? So
Yes,
idea
sir.
is clear what we are doing here. We are generalizing whatever we have done till now. We have model linear regression, we have model logistic regression. Now we are generalizing these things. That's it. So any questions till now, till here?
Hello.
Yeah.
Sir, I'm still unclear about the part where you say that our model is.
Sorry. Can you please little louder?
Yeah, I'm still unsure about the part where you say our model is the expected value of y given x. Like.
Okay. The second.
So in the logistic regression, you showed that our model is P. So if a new point comes, I will just like do what with it?
So my point is that any new examples comes in, okay, I don't know what value it takes, okay, but I know that it is coming from this normal distribution, normal 0 1, okay, I don't know the x, but I'm to predict what x can be. So what value you will give to that x? Suppose you don't know what is x, and now you have to assign some value to x, but only information you have is that x is coming from distribution normal 0 1. Now you have to predict some value for that x. So what value you will predict for that x? It can be anything that I see, that I understand. It can be anything because it's coming from normal 0 1, so it can have any value from minus infinity to infinity. But as I know that expected value of normal is 0, so I will predict that because there is lots of more chances that it can have 0. Remember, normal distribution is the 99% chances that is coming from minus, or around 67% chances that is coming from -1 to 1, right? And around 95% chances is -2 to 2. And expected values of normal is always that mean. So I will suppose that it's more most chances is that the x will have value 1. Okay, so actually we are predicting the expected value of that distributions. That is our model.
Okay, sir. Yeah, understand. Like, got it.
So does this mean, sir, that you're calculating the posterior based on the prior, based on all our previous discussions? Like considering that we've run through the model, the data, we know that this particular thing belongs to this class, and then based on that, we decide that this is the expected value.
Yeah. Because once we know that data follows some distribution, now I'm to predict something. So I will predict the expected value. That's it.
Okay.
Very easy to say. Let's say there are two cases: linear regression and logistic regression. These are the two things you have read in week 5, I guess 4 and 5. So in case of linear regression, once you build a model, we have to apply it on a test data set. So what are we doing? We have been given feature vector x. Now we have to predict what the y is. So essentially it is, what is my y? So I'm predicting the house price given the two features that we discussed in the videos, right? Somebody has given us the number of rooms, how far it is from the station. These 2-3 things are given to predict the house price. So essentially the regression model is nothing but prediction of house price, which is y, given the feature vector x. So that is our model, right? That's first one. Second one, in case of logistic regression, either we have a binary classification or a multinomial classification, either 2 levels or 3 levels. In that case, all we are doing is we are predicting conditional probability. If we have been given a feature vector, what is the probability that it belongs to class C? Right. So if the probability is higher for a particular class, then we'll end up allocating that prediction to that particular class. I think that was one of the graded assignments, right? So in all these cases, essentially the prediction is expectation of basically what is distribution y given x, right? In both the cases. Hopefully, I don't know, Parth, if it helps clarify your question.
Yeah.
Okay. So now we have seen linear regression, logistic regression. Now let's come to the last one, which is softmax regression. Okay, so softmax is missing here.
Just one question on linear regression, right? I don't know if it's a stretch of imagination there, because the expectation of y given x is mu.
Okay.
Does that mean that the W transpose automatically W weight vector is like a probability of each of those features?
No, the weight vectors won't be the probabilities. Weight vector are not the probabilities. After passing through the that sigmoid function, that values that are coming, those are the probabilities. Weights are not probabilities.
No, I'm talking about linear regression.
Okay.
Because we are multiplying the weight vectors directly with each of the features to arrive at the label, which is a continuous variable.
Okay.
does the weight vectors turn out to be probabilities? No, right? It's just
No, so
weights.
probability of what? So you are saying in the case of linear regressions, weight are probabilities. Probabilities of what?
Yeah, okay. They're just acting as weights because each one are individual features. Okay.
Yeah.
No, I'm just thinking of
Kaushik,
calculating the expectation.
Kaushik, if I may add, what we're saying is W transpose X is a random variable, which belongs to a normal distribution. That's why you get a mu.
Yeah, exactly.
Right. Okay, yeah, thanks. That helps.
So maybe what when we make a prediction, that is the expectation, but there is a distribution around that prediction. So if you do a confidence interval around your prediction, then the distribution and other things will come into the picture. Probability, what is the chance that your prediction will lie within a particular interval? Then the probabilities will come in. Otherwise, generally in regression, we are expected to predict on an average what do we expect this y to be if somebody gives us the x.
Yeah, got it.
Okay. So how many of you have gone through the softmax regression? It's just the extended version of the logistic regression. In the logistic regression, we have only two classes, 1 and 0. In the case of softmax regression, we just extend this notion to the multi-class classification, right? And we model this thing. So now we will see that softmax regression is nothing but it's actually a standard case for GLM, special case for GLM. Okay, so this is missing out here. I don't know why. I've already done this thing. So I will make use of slides now. Okay, give me 1 minute. Let me open the slides. Okay, so can you see the screen? Generalized linear model?
Yes.
Okay. So these all things we have seen. Okay, one thing here, something I think already someone had mentioned. One thing was wrong here.
Yeah, it said P is equal to 1 minus E.
Yeah, that. Which one was that?
It was the previous slide, right at the beginning.
Maybe Bernoulli, right?
Yes.
I think that exponential of negative half in the corner.
So this becomes, if you solve this, if here 5 becomes 1 upon 1 plus e raised to power minus theta. It's not 1 minus. So it's just a mistake here. So yeah, okay.
Could you repeat that, please?
So it's just mathematical mistakes, just a silly mistake here. It's 5 equal to 1 upon 1 plus e raised to power minus theta. It's plus here in the denominator.
Okay, it actually should be plus, is it?
Yeah, it's plus. It should be plus. Here's mistake in the slide. Okay, so this we have seen logistic regression, seen softmax regression. Okay, so what is softmax regression? Here we extend our notion to the multi-class classification problem. So we suppose that by takes value 1 to k. Okay, so as by takes values 1 to k, so it we assume that it follows the multinomial. It follows the multinomial distribution. So it can be categorical as well. So what is the difference between categorical variable and multinomial distribution? What is categorical and multinomial distribution?
Multinomial was essentially like
What is Bernoulli and binomial?
Bundle is individual trials, and binomial is if you add up all the trials. Yeah.
The same is categorical.
Yeah.
And multinomial. So in Bernoulli, we have two outcomes: success or failure, right? And what happens here? Here in Bernoulli, we are interested in the finding the probabilities of outcomes 1 or 0, right? What is the probability of 1 and what is the probability of 0? So this is our PMF. This is called Bernoulli. In binomial, what we do, we perform our Bernoulli trials for n number of times. Let's say we have performed this trials n number of times, so n is fixed here, and our interest is we count the number of, so x becomes the counts. So here we are interested in how many times success occur, or how many times failure occurs. So these PMFs become if we are interested in this kind of PMF, we say that it's a binomial. So here we are supposing only two outcomes, success and failure. But in our case, if there are more than two outcomes, so let's say their outcomes are 1 to k, then if we are interested in these probabilities, so x becomes whether it is 1 or not, 2 or not, so something like that, then it becomes categorical variable. Okay, so categorical will say if x has values 1 to k, so what will be the expected values of this? X equal to 1. So what is this? Whether x is 1 or not. So it will become p. If so, let's say the probabilities of this one are p1, p2 up to pk. So these are my parameters here. So and obviously sum over all those I equal to 1 to k will become 1 because these are probabilities. So what will be the expected value here? It will become for 1 it will become p1, for 2 it will become p2, and up to pk, right? Now, so here in categorical we are interested in the finding the probabilities of outcomes. But in the case of multinomial, if these trials are performed n number of times, let's say we have n is fixed here, and we have performed. Now we are interested in what is that x will take. X is equal to 5. So for let's say xi, x1, x2 up to xk. So what is means? It means that what is the probability that in that n trials 1 occur 5 times. This kind of distributions is for it comes from multinomial distributions. Okay. And one more thing you can remember the expected value here. So expected value of x1 x. So let's say the distribution are x1, x2, xk. So the expected value becomes here it become n. N is total number of trials. So let's say small n only. So it's n p1, n p2, and pk. Okay, so these are the expected values. Okay, so that's the same thing like Bernoulli to binomial, categorical to multinomial. Okay, so as our distribution are coming, our values are coming from 1 to k, we can assume that it follows categorical distribution or multinomial depending on what how we are interested in, what values we are interested in. If we are interested, we have n data set. If we are interested in probability of each outcome, then it is categorical. And if we are interested in how many times 1 occurs, how many times 2 occurs, then it becomes multinomial. So actually multinomial categorical is a special case for multinomial distribution where we have performed only one times. We perform the trial only one time. So categorical is a special case for multinomial distribution. Okay, so here we are assuming the parameters to be phi1, phi2, phi_k. It means the probability of p equal to 1 is phi1. Probability of p equal to probability of x equal to k becomes phi_k. As their probabilities some become 1, so we can say rather than k parameters there are only k minus 1 parameters because ultimately sum is 1. So last one you can say 1 minus phi over k. Last one you can say last parameter you can say that it's a 1 minus summation over phi I varies from 1 to k minus 1. So there are total k minus 1 parameters for this distribution. Okay. Now, so I'm representing those in the form of vectors. So these are notions. So just remember these notions. We are gonna use this thing. T1 I'm calling 1, and other other. It's a vector of shape k minus 1. K minus 1 into 1. I mean the k minus 1 rows and 1 column. So if it is it belongs to class 1, then vector 1. If it belongs to class 2, then entry 2 is class 1. Other entries is 0. And it will, if it belongs to class k, then all the entries are zeros. Okay.
Sir, why in class K all the values are 0?
Because it's a vector of k minus 1 cross 1.
So, but why can't we just take
we can also do that, but so here we are assuming only k minus 1 parameters, so we are sticking with the k vector of k minus 1 cross 1.
Is that we're doing that because of computational?
Because you can say we are just getting rid of the dependent feature. That's it.
Sir, I think because of our assumption, right? Because it's a mutually exclusive and exhaustive, all the probabilities have to add up to 1.
Yeah.
So if I have a variable with 5 classes, once I estimate my 4 probabilities, P1, P2, P3, P4, the 5th one I don't need to estimate. It is 1 minus sum of all the 4, right?
Yeah.
It's a restriction. So we don't need the last one.
Yeah.
Because
so
it has to be equal to 1
that's
minus
the only
sum
reason
of
we are
all the
sticking with the k minus 1 entries here.
Yeah.
Not with the 5th, because fifth one is already clear. If we know k minus 1, if we know that all are 0, then last one automatically become 1. Okay. You can also stick with the k vector of length k, but it's again the same calculation will be there, but just become more lengthy, more you can say more mathematically. That's it. Just to get rid of this thing, we are assuming there are k minus 1 parameters of the distributions rather than having k.
But
right?
sir, if we get an example of the last class, then how do we predict for that particular thing?
Sorry?
If we get an example of the last class, that is the kth class, then in that case, how do we calculate all of these and then we find these? I mean, how do we come up with the final predict?
So if the predictions is making it's not these are not the final values, these are not the probabilities. Here I'm just denoting if it belongs to class 1, then it is first entry is 1, other zeros, and if it belongs to class k, then all the entries are 0.
Okay, so that's what I said, sir. Once you've done this training and then you get in the test data, you get a example of class K. Then okay, how does it implement it actually? I couldn't understand how would that process happen.
Okay, so actually I didn't get your point. Which procedure you are talking about?
Sir, this is all the labels that we have, right? This is basically one-hot encoding that you've done for all the labels, all the classes that we have, right?
Yes.
So I'm saying that we are doing only for k minus 1 classes. Because the kth class, we assume that k minus 1 classes would give us the kth one.
Yes.
Suppose if we get an example of the kth class to be predicted, how would that implementation happen is what I'm confused about, sir.
Okay, I got your point.
So has sir implemented this that way only in the collab, like using k minus 1 classes? Something.
Yeah, so how that predict is happening actually behind the scenes, I couldn't understand how that works.
Like even I don't understand this part. I was just
pardon?
Like, did you have a chance to go through the collab implementation?
Yeah, I did, yes.
So sir, has sir implemented it this way, like for the k minus 1 classes, or just he took
no, in the here we are only showing that it is a special case of that GLM. That's it. We are not implementing in that way. Actually, our implementation way is what we just take k linear models. I mean linear combinations, k linear combination, and pass through the software function. We check which value is greater. Right. That is the way of implementing a model.
Yeah. Yes, sir.
Model.
Yeah.
Right. Here we are showing that model is actually a part of GLM itself, GLM only.
Okay. So probably as Parth is saying, I'll go through that collab again probably.
No, Sunita, I haven't been through the collab too. Like I was just asking, like if sir has implemented it this way or.
Sir has implemented it, but what I couldn't understand.
No, sir has implemented in that manner only. That make k combinations for k classes, pass through shortness function, check which value is greatest, highest. I mean.
Just that he is. If I recollect right, I don't think he has specifically found out k separately. I think he's probably had like similar to a dummy feature. I think he's got a particular weight and then calculated for the whole thing. That's my recollection of the code, but maybe you can take a look at it again. I don't think he's given a special treatment for K separately.
Okay, I'll have to go through it again. Even I don't recollect too much of it, but yeah.
In real life, what happens if you have a label vector y with k classes, you do a frequency analysis. The one with the lowest frequency, you make it class k because that is of least interest to you. And then, so
no. Can you please repeat what you are saying, please?
So let's say I have a dependent variable y which has 5 classes. When you look at your training sample, you do a frequency analysis. You choose the class with the lowest frequency as your reference, like a kth, because that is of least interest to the researcher, because you are more interested in high frequency class. Unless your interest is lowest class, then so whatever is of least interest, you make it as k. Then essentially your model is looking at the ratio of log likelihood between the class of interest and the reference class. That's typically how it works.
Okay, yeah, that makes sense actually.
Okay.
Yeah.
But actually, I don't really get the point of this fact that is being shown here. Like, what is the use of this particular fact?
It's a representation, right? So your y has to be expressed as a n cross k vector, right? I mean, matrix. So these are things that are part of that n by k matrix.
Yeah, but the fact that all the we can calculate the kth class probability from k minus 1 classes, how does that help us? Like, it's just a one dimension reduction. So I don't think that would significantly affect the computation too.
Let me add one point here. Okay, so this kind of calculation we are doing just for bringing that software function into the kind of form e raised to power by in that form. If you remember, b by e raised to power minus eta, eta transpose of t of y, right? That kind of form we are trying to bring in for that multinomial distribution. That's it. That is the motive here. We are not in actual, we are modeling in the same way. We assume k linear combinations, we pass through the shortness function, and we'll check which is the highest value.
So okay, if we take k classes,
these manipulations we are doing just to bring that into the exponential family. That software whatever the distribution is, multinomial distribution is coming from the exponential family. That's it.
So that means if you have a training observation, you'll create a vector with, a vector with k numbers. The number with the highest one will assign that class to that.
Yeah, and your point was
the whole idea, right?
Seeing that last one we took as the reference, and then we will check. In the case of Bernoulli, we take or success upon failure. In our case here, we assume last one as the reference, and we make the upon the last one, right? That was your point, right? Okay, let's go ahead and we'll see about these t by r, how these t by r t's are coming into the picture. Okay, so indicator function, right? If the event is true, then it gives 1. If the event is, the input events are false, then it gives the value 0, right? So if t 2 equal to 3 is not true, so that indicator function will give value 0. So that is, we all know what is indicator function. So what is t of bi of I? So here t of bi of I actually denoting the ith element, right? So ith element is actually gives the count for that, actually gives the probability for that outcomes, ith class outcome, right? So what will be the expected value? The category, what is the expected for categorical distributions? It's just that probability of that bi of I, right? So we are denoting this probabilities to the phi. So expected value of t of bi of I, right? It's nothing but that phi of I. Now, so what is our distributions? Distribution says that, so what is in Bernoulli? Remember in the Bernoulli, we have done p raised to power by 1 minus p raised to power by 1 minus pi, right? So here in the categorical distribution, we do p1 raised to power that if it is by equal to 1 or not. Okay, so remember only one of these gonna be true. If is by equal to 1, then all these indicator functions will give 0. Only this one will give value 1. So probability will become 5, 1. Let's say example is coming from the class 2. So only this indicator function 1 of y equal to 2 will give value 1, and all other will goes to 0. So this is the probability, right? So it's just we have write in concrete way that expressions of probabilities PMF we have write in the concrete way. Okay, so now okay, now it's just a mathematical manipulations here and there to bring out into this form, last form. Okay, so if you do this manipulations, it's very easy. You can check it out. So last PMF comes out in the form of okay, the form is not given here. So if you look at this form here, okay, so okay, let me see whether the last expression is given or not. Okay, so last expression is not given, I guess.
Last expression is in B of Y, that one is it. That's there in the last.
This one. So this has this form. Only you need to compare these things. Okay. Yeah, so you can compare from here. So it's the vector product of last. Look at the second last expression. This is T of by 1 log of phi 1 upon phi k. So this is the vector product of what? T of by and next this vector eta vector and the vector that T that we have already defined. So if you take the product there, so this expression comes, right? So we can say that from this expression, our eta is this vector. T we have already defined and this expression, right? So minus of something a of eta. So here a of eta become minus log of phi k. So eta become not eta. A of eta becomes minus or plus. It should be minus, right? So yeah, so a of eta become minus of phi k here, and by is constant therefore. So we have the nice form here. So from there we can say that the multinomial distributions comes from the class exponential family. Okay, so what is eta? So eta is a vector whose ith component is actually log of phi I upon phi k, right? Same kind of form as the odds, log odds, as we have in the Bernoulli distributions. Okay, so last one becomes so of the eta, last entry becomes 0 because it's a log 1, right? So did we define link function before or not? We didn't, right? So let's see what is link function. Where all these we defined?
So one doubt I have, what do you mean by this canonical? What does that term mean, sir?
Canonical. That I'm also not sure why it is called canonical. Natural means natural. It means that it has it gives the characteristics about the distribution. That's it. That's why it is called natural. Why it is canonical? That I'm also not sure. Let me just Google it out.
Sir, I also tried to Google, but then it gives some like English meaning about it. I didn't get what actually that here it means.
Yeah, the meaning why it is called canonical, that I'm also not sure.
It's written, it's called the simplest form of something.
What?
It's written on Google, it's called the simplest form of something. Like
canonical
simplest,
means?
Yeah.
Okay. There we have defined that link function and response function.
Sir?
Yes.
There is another slide, I think. There
Sorry?
are two parts of slide. You have opened only one part of slide. There are two parts.
Two parts. Next one
Yes,
is for KNN. Yeah, this one. So a function of a natural parameter is called canonical function, right? So and that inverse of that is called link function. So function of eta is called response function, and the inverse of that is called canonical function. Okay, so in the Gaussian family, remember our model was eta itself, so mu itself. So that so eta was mu, so it's an identity function. In the case of logistic regression, in the case of Bernoulli function, what was our expected value? It was 1 upon e raised to power minus eta, right? Eta x. So 1 upon e raised to power minus eta. That function is logistic. That logistic function is response functions. So inverse of that is called link function, and that function of eta that gives that is actually same as the expected value of t of bar given n. So it's gonna be a function of eta. So that is called response function. So in the case of software regression, so what is expected value now? So we are going to define invert the link function and derive the response function. Okay, so because it's invertible, so the invert of response is link and invert of link function is response function, right? So this makes sense. Invertible of inverse of inverse of function always makes sense, right? So e raised to power minus eta is already defined. So because eta I be defined as log of phi I of phi k. So eta of e of raised to power eta I will become this thing. Okay. So if you manipulate this thing, phi k comes here. So phi k e raised to power eta I become phi I. And what is next? Okay, we are summing over I, all over I. So phi k will be phi k will be common in all the terms. So we can take out phi k from all the terms, and we can sum over I over 1 to k. Or so these are probabilities, so it will become 1. So from here, phi k is coming out to be 1 upon summation over all the e raised to power eta i's, right? If you put this value here, so we have come through e raised to power. Okay, so if you put phi k value here in the first equation, phi I become e raised to power eta I upon summation over these things, right? So this is a function of this. Or remember our expected value by those probabilities P1, P2, all these were the expected values. So this is called the response functions. Okay, so this will become our model. This becomes our model. So but that has the same form, right? That we have derived earlier in our model Monday session, right? So from there we have seen that actually software regression is also a part of GLM, because the same model we have, right? And we have defined only using those conditions. Here the distributions are multinomial rather than Bernoulli distribution. Or simple to say categorical rather than saying multinomial. Okay. So,
sir, I had a question here.
Yes.
So softmax is basically like a normalization function, right?
Yeah, actually logistic or this both the functions are the normalization functions.
Yeah. So here we're trying to normalize a vector of probabilities of each class level.
Okay.
So why use the softmax? Why not just sum them all up and divide them by the individual values?
Why do we don't sum up and divide those, huh?
Yeah.
So if you do that kind of thing, sum over all those values and divide by this, that functions will not give some definite model, definite or say hyperparameter. So remember, linear combination is actually hyperparameter. Once you pass it through the logistic functions, it takes value 0, 1. That is okay in our doing sum and then divided by over sum. Then it also give value 0, 1. But that will not have any nice form. But we want to bring that into the squeeze kind of form. We will just squeeze that hyperplane into S kind of shape. That shape is actually a function that is called logistic function. Okay, so actually what happens in the logistic regression, let's say you have these kind of these classes and you have this model. Okay, so your classes are your data points are distributed something like that. Okay, so these are your two classes data point, and what we find by doing the linear combinations of features, we model something like that. Okay, so what logistic function do? It just squeeze this is hyperplane into some S kind of thing, this kind of thing. Okay, because we are not predicting values, we are predicting the classes, and then it becomes 0 to 1. In 0 to 1, one more property of logistic function is that for so what is logistic function? Sigma z is 1 upon e raised to power minus z, right? So what one property is that if j is higher, then this becomes if z is higher, then this value becomes short. I mean this value become very low. But when z is very low, very small value, then sigma z is again becomes small value. So this is one properties is that. So it means that if we are close to the hyperplane, then the value itself it predicts something like that. If we are far from the hyperplane, I mean in the case of what they call in the case of if we have some noise in the data set, so that noise is actually reduced because we just squeeze that values to close to in the interval 0 to 1. So this is one property of logistic function. So just because of these two properties, we use logistic function rather than just simply summing over and dividing over.
Yes, sir. Excellent. Thanks. I didn't think that.
Okay, so this is for generalized linear model. So only keep in mind that we are only generalizing our things. Whatever we have done till now, we are just generalizing these things. That's it.
Sir, with softmax regression, if we had only two classes, will the shape of the curve look like a logistic regression only, or how does that?
Yeah, it should be logistic regression. It must be logistic regression.
But the activation function looks very different, right? It's e power something divided by the sum over e
that will become same thing, right? That will become same thing.
Okay, I'll have to try and see.
It's not hard to see because in the softmax what happened, e raised to power linear combinations upon summing over, right? All the classes. If you have two classes, let's say class 1 and class 2, then okay, so yeah, that part I missed in the last section. Okay, so what happens? So there, let's say only two classes 1 and 0, right? So there logistic regression we only define only one linear combinations, remember, right? But if you go through this procedure, softmax regression procedure, so in this case what we will do, we will define two linear combinations, let's say Z1 and Z2, Z1 and Z2, Z0. Okay, so this will be some linear combinations, let's say W1 transpose X, and I'm adding Bayes term inside it. Okay, next will become W0 transpose X. So if you find out the softmax regression from here, so it will become e raised to power W1 transpose X upon e raised to power W0 transpose X plus e raised to power W1 transpose X, right? So if you take this term in the denominator, so this will become 1 upon, so this term will become 1 plus e raised to power something. Okay. So actually this has already come into this kind of form.
Right. So both of them.
So rather than doing two things, because what happens if you do two models here, so what will be the property of this? Because the sum over is always 1. If this value these values is getting close to 1, this value will I mean, if this values go close to two values will pass, right? One for this thing, and so this will be sigma of 1, right? And sigma of 0 will be e raised to power W transpose X, and denominator will be the same thing, right? So these two, if this values goes close to 1, this value will close to 0 because these are probabilities, right? Sum is always 1. So what happens if we draw these curves? So let's say this is 0 and 1. So if the curve of this thing is something like that, though the second curve will automatically will be something like that, right? This sums will always gonna be 1. This sum plus this sum is always gonna be 1. This gun is always gonna be 1. Okay, it's hard to visualize this thing in the more than 2 dimensions. So here we have only 2 classes. Then you can see if one model is coming in this shape, the another will automatically will come in this kind of shape. So these sums, if we are here, this sum plus this sum is always gonna be 1. This height is gonna be same. Okay, so automatically these models will look something like that. So rather than defining two models, we can do in only one model itself. Just define one model this model, and if it is greater than 0.5, let call it class 1. If it is less than 0.5 is less than 0.5, then call it class 0. Okay, so in the case of two classes, you need not to define two different models. You just define one that will work. But more than two classes, you have to define 3 combinations, 4 combinations, depending upon how many classes are there. Okay.
So if there are k classes, we have to define k minus 1 combinations.
No, k combinations.
Because the last one is not needed, right? That's what we learned.
Yeah. But it's better to define k minus 1, because otherwise that calculations will become very messy kind of thing.
Okay.
Sir, one simple question is that since the graph has your the 0.5 portion is shifted toward that the axis, is that any meaning of that shifting axis here? Because that formula is always e to the power I divided by 1 plus e to the power I. So in that case, I is our data. So isn't it? It will be that 0, then it will become 0.5.
This curve you are talking about?
Yeah. So I'm thinking that it is that always it will be 0 on that 0.5. It will be always on the 0, or it can be the shifted. If it is the shifted, then what is the situation?
Okay, you are talking about if the probabilities come to be 0.5.
Correct. Yes. In the previous.
Then it's a tie kind of case. If you have probability 0.5, so you have to decide. You can just randomly assign any of these classes, 1 or 0. But stick to one thing only, one model itself. If it is, let's say, if sigma z is coming out greater than 0.5, let's call it class 1. And if it is less than 0.5, it's call it class 0. So you can include 0.5 into class 1. It's just a random thing. It's not just any rule that why we are including, because it's a tie here. There's equal probability that it may belong to class 1 and class 0. So correct, in that particular case, you can assign any of these classes, but stick to any of these. So in our course, we are sticking to this particular case. Stick to class 1.
Okay, so the shifting of the graph doesn't matter here. That the numbering on the x-axis line. Suppose there is a two value, x and y. Then numbering on the x-axis doesn't matter. It's the graph is independent.
No, here you have feature. Now here you have log odds. Actually, sigmoid functions. There's sigmoid function, sigma of z.
Okay.
So, sir, like we can set thresholds in logistic regression.
0.5.
No, we can set custom thresholds.
Right? Yeah, this threshold you can also define in your way.
Yeah. So does it make sense to do that here in softmax?
In the softmax?
Yeah.
No. Here in logistic regression, you only define one linear model, right? One linear model, and then you have to decide threshold. If greater than something, then it goes to class 1. Yeah, in the softmax, what we do, we define k different, and the k different values comes out. Sigma z1, sigma up to sigma zk. Okay, so we assign the highest to, we assign that example into the highest value, class taking highest value. Okay. So I think we should move now to the KNN. Softmax regression and that GLM is done. So have you done KNN? Have you seen the lectures? KNN is pretty easy. Just check the neighborhood. It happens in the behavior as well. You just check the neighborhood and just predict that he will be the same as their neighborhoods, right? So that's gonna be our do in the KNN. So KNN is actually instance-based learning. What does it mean? Instance-based. So KNN is parametric or non-parametric? So KNN is non-parametric. That is, we don't make any assumption about the distribution of the data set. So as far as we are making assumption that it comes from normal distribution from Bernoulli distribution and all, but in the case of KNN, we don't make any assumption about the distribution of the data set. That's why KNN is called non-parametric. Okay, one thing is that KNN is non-parametric, so it is non-parametric. Second thing, it is instance based. What is instance based? So one thing here, we don't have any model here. So every time a new examples comes in, it checks its neighborhood. So let's say we have training set and data set, training data set. Any new examples comes in, it checks the neighborhoods. So how to find the neighborhoods? Is check the distance from those points. So let's say we are defining two distance, Euclidean distance and Manhattan distance. So any of these you can choose. So we check how k number of k neighbors for that data set. Let's say you have these classes, these class 0, and these are coming from class 1. Okay, so what happens, any new examples comes in, let's say this is your new example, so it checks the neighborhood. So you will check the Euclidean distance from all these data points and check. So now I'm designing KN 3NN, so I will check 3 neighbors of this class. So let's say first, second, and third, these are my neighborhood for this example. So I will say, because the majority are the class 0, so I will predict that this example belongs to class 0. Okay, so this happens in the KNN. It checks the neighborhoods and majority of the class bins. Okay, so here majority of the class is class 0, so we will predict into the class 1, right? This is called instance based, because every time a new example comes in, we don't have any separate model. In the case of regression, we have model, we have just fit it. Once we have fit this, any examples comes in, we just put this value and just predict, right? But here we don't have any model here. Every time a examples comes in, every time we check the similarity here. So we check similarity or dissimilarity. Here we already always define similarity. Similarity means whether they are in the class 1 or class 0, depending upon the distance. Okay, so distance, we define three neighbors here. If we modeling 4NN, then we will find four nearest neighbors. So let's say 3 comes from class 0, one comes from class 1, then we assign that example belongs to class 3. That's it. So that's what happened in the KNN. We just check the neighbor.
This would be taking a lot of time, right? Every time you pass an example.
Yeah, every time. That's why it's called instance based and lazy learner. It's also called lazy learner. Lazy learner means we don't have any functions to fit here, any model to fit here. So every time it comes in, any example comes in, then only it checks the similarity or dissimilarity, whatever we are finding, right? And then we find the neighbors, and who just check according to the neighbors, we just assign the predict value. So that's why these are called lazy learners as well. Okay, instance based, you got it. So
but it has to calculate the Manhattan distance to every other point in the list, is it?
Yeah, so if you are using this distance measure, then you have to find Manhattan distance from every training data set, and you have to check if you are taking k equal to 5. So you have to check what are the minimum 5 example with the minimum distance.
Okay, so we calculate the Manhattan distance to every point and pick the 5 nearest.
Every point. Then we'll check the 5 lowest distance. Okay. So this happens in the KNN. Just check the neighborhood, who wins. Just check the majority, and who wins with the major class. So in the case of regression, so this is in the case of classification. But in the case of regression, just check the neighbors. Let's say we are interested in 5NN, then we check 5 neighbors and just we take the mean of labels, right? 5 labels. That's it. So this happens in the KNN. So remember, this is non-parametric. We don't make any assumption about the data set. It's instance based. Every time it's a new example comes in, we check the similarity or dissimilarity measure, and then find out the 5 k neighbors. depending upon if it is regression, then we will take the mean. If it is not, if it is classification, we check which points in the neighborhood, which points are of major class, and we predict into that class. That's it. That's happen in the KNN. Okay.
Sir, few question here. Can I ask?
Yes, sure.
Yeah. So the first thing is that to take that 5, suppose the k is equal to 5, then take the minimum 5 distance. I have to run through the entire point, no?
Entire point here. Every time a new example comes, you have to do entire process again and again.
So but in the programming, in the scikit, it is already optimized this thing. I don't have to do this thing. I just call the function and it will work automatically. So I don't have to do manually run that, find the distance of the every point. So
You can do a for loop, right?
Pardon?
That is coding part. That you have to do. Obviously, that you have to do. If you are doing manually, then obviously for n data set you cannot do. You have to write a code to find the distance, to find the 5 lowest distance examples. That for finding this, you have to write the code. It's not you can do manually.
No, Kumar,
Okay.
in scikit-learn, it does it automatically. There is a library for that. Yeah.
Yes.
Scikit-learn implement automatically. For all the models, it does work for you.
And so
You
that
just
is
have to
actually
find the
the
parameters
simple.
there. Okay, so one thing, how to decide k. Which value of k will you prefer? So k here is a hyperparameter, right? So how you will find the best value for k?
So if you have some kind of a metric and to optimize hyperparameter, I have to plot that error
Yeah.
function
So
or
for
something.
hyperparameter, you have hyperparameter tuning, right? Hyperparameter tuning. Okay, so what we can do, we can start with for lowest value, and then we can go up to some k value, and then we can check the on the validation test what is the error. Okay, so if this kind of error is coming, so for this k value, it's, let's say k equal to 5 is coming this. So in lowest error, we check it is coming for k equal to 5, we choose k equal to 5. So here it is hyperparameter tuning. You have to set values of k, and you have to find the validation curve and all. You have to check for which value of k if the validation error is the lowest. Okay, so that's how you choose the k, because it's a hyperparameter. So always remember, in hyperparameter cannot be set manually. I mean, we always set manually, but there's no any hard and fast rule that k should be this thing or any hyperparameter should be this thing. So you have to find that what should be the best thing for that hyperparameter, right? So k here is a hyperparameter. Okay, so now come to the overfitting and underfitting. So what do you think for k? Let's say you have you have n number of examples. Okay, and you choose k equal to 1. Only one date. Buns means only one neighborhood you check.
Underfit.
So it will underfit or overfit?
Underfit.
Overfit.
And for k equal to n, you have n example.
Overfit.
So for lower value of k, it may overfit.
You memorize all the data, right? So that's
it. And for the higher value of k, it may underfit. Because remember, for the lower value of k, the training error will be less, but the test error can be higher, right? So let's say k equal to 1. So training error is always gonna be 0. And for if we keep on increasing, the training error can go on up and the test error go on lower, right? So when k become n, means k become n, then what will be the prediction here? So you have n examples and you are setting k equal to n, then what will be the prediction? So you means you are finding k nearest neighbor. So all are the nearest neighbors, right? So what will be the measure? You just whatever the major class is there, you just predict it. So every example there, every training set there will be predicted to in the only one class, right? So their training error will be higher. In that, if you set k equal to high value or k equal to n, then in this case training error will be high, will be highest.
Sir, can you discuss one thing here? Because that in regression, what's happened that, can you hear, sir?